We actually need to go a bit further, and this is why Jim Dolan and I didn't do this. We didn't realize that when you're doing something right, you should keep on doing it. I mean, we realized in general, the general principle in mathematics, that if something works, you should just keep doing it as much as possible and see until you run into a wall. So we had this wonderful idea of spans of groupoids, the advantage being that you can turn them around, unlike a functor. But we never thought about spans of spans. That is, we looked at maps between spans, where we had an arrow going from here to here. But you could look at a span, you could replace that with a span too. And the advantage of doing that is that now you can turn those around as well. And in quantum mechanics, it's really important to turn things around. That dagger category structure I'm talking about is the basic idea that whenever you have a quantum process, there's a reverse or adjoint quantum process going back, which is not necessarily an inverse operator, it's an adjoint operator. And basically in quantum mechanics, there's sort of no built-in arrow of time. You can, in the formalism of quantum mechanics, a process is not a function. In the literal sense, it's something that you can reverse always, even if it's not invertible. And that's what this is letting us do for the maps between spans. Now we work with spans of spans. So what they did is they said, let's look at that isomorphism or equivalence, I guess, of spans, and you can break it apart into two pieces. So this is a kind of coproduct here. So you can break it into two parts. The first part going from here to here, and the second part, let's call those I and J. But now, so I could have done that already, but now using spans of spans, we can flip these around, take their dagger, and get spans of spans going backwards. So these are sort of like inclusions, and these are like projections. And it turns out that to write down the relations in the categorified Heisenberg algebra, you really need to talk about these, I dagger and J dagger. So that's why working with spans of spans is crucial. Let me just give you one extremely boring example of one of these relations. In a way, this is bad because you may think that it means that all the relations are completely boring. But of course, boring things are easier to understand. So I want to do one that's easy to understand and that I can remember. So at left is the way that Kovanov wrote it. Oh, sorry, wrong thing. I'm desperately fumbling around looking for. Here it is. Sorry, yes. Sorry. So, yeah, I'll steal anything. Let's press the button, see if it works. Yeah. So, yeah.
Well, you press that button, you start hearing your own voice.
Oh, okay. Yeah. So here's a really boring example. So this inclusion I called I, that's the inclusion of A dagger in A dagger A. Remember, roughly speaking, this is really a summary of a span, but you can think of it as all the ways to first take a piece of chalk out of the box and then put one in. And those are included in this larger collection, all the ways of putting one in and taking one out. For every one of these, you get one of these.
Excuse me to be clear. This A dagger, for instance, is an object in some category, and the arrows are morphism.
Of course, everything is an object in a category. But so it's sort of. But no, I'll be more informative than that. I don't want to just stop and say it. So there's this groupoid of finite sets, and there are things like this span that I'm calling the creation operator. So it's actually a span, where here I'm adding one extra element, and here this is the identity. So this A dagger is short for a span, and then here what I'm doing is I'm composing two spans. So that's again a span from S to S. These are the basic building blocks, these two.
So when you go from the category.
Wait, let me finish. I'm not
Yes.
not done. So those spans themselves are actually morphisms, right? They're morphisms from S. I'm working with a situation where I have groupoids, spans between groupoids, and then spans of spans. So those are the objects, morphisms, and two morphisms. So the reason why I'm drawing these things as double arrows is because these are two morphisms. So these are short for spans of spans. This is an actual map of spans, a way of including any of these processes in these. And this is the thing we get when we turn around that map of spans. Yes, you were saying? You had another?
So would you like to call that some kind of categorization? Or this is not exactly the same. And
Categorification.
What we're doing is we are taking the Heisenberg algebra and we're categorifying it, by which I mean that instead of the Heisenberg relations being equations, they're now isomorphisms, and the main isomorphism is that I'm thinking about here is this one here. This. But now that isomorphism satisfies new equations of its own, and I'm trying to explain an example of one of those equations involving this isomorphism. And that's the new layer of structure that Kovanoff discovered.
But the strange thing is that, in fact, you are not adding any information because you have the same structure, but you are looking at it in a more elaborate structure. And then you go from a situation where you have some kind of commutativity, which means time reversibility, to a situation where you are irreversible. You understand what I mean? This is very strange.
Well, I don't know quite what you mean by that. So
Because
in quantum mechanics, you have linear operators. They aren't all invertible, but they have this magic fact that you can always take their adjoints and get an operator going back. And so what Morton and Vickery did is realize that we can make that happen at the next higher level if we work with spans of spans. So now we can not only reverse any span, but we can also reverse any of these spans of spans. So we get this kind of ability to take adjoints or daggers at both levels in our two category. And somehow that seems to be what you need to do to make it act like quantum mechanics, to make that's a vague comment. So I just wanted to explain why this was true. It's actually not so hard. So these very intuitively, these are the processes where you take something out and then put something back in. Those are special cases of the processes where you first put something in and then take it out. But then we can project down from the more general case back down to the special case. That's where this dagger of the inclusion comes in. And it turns out that including and then projecting is just the same as not having done anything at all. That you get the identity span of spans. So Kovanoff had a way of drawing this, which looked like this. So for him, a downwards pointing line was a annihilation operator. So this A here is this downwards pointing line. An upwards pointing line is the creation operator. This process of switching, that's drawn here, and then switching again, that's drawn here, and it's equal to the identity, which is this vertical pair of lines. So this is just a kind of notation for the same thing. Which, yeah. So if you start with a way to take one thing out of a finite set and then put one in. Oh, there's a typo here. I relates this to a way to do it in the other order, and then I dagger gets you back, and you get back to where you started. The point is there are other relations that are much more interesting than that. So basically that's where I'll stop. So what we have here is some signs of something new going on, where we can replace Hilbert spaces by two Hilbert spaces. Once extended TQFTs are replacing TQFTs, or subsuming them, I should say, including them. And the categorified Heisenberg algebra is subsuming the original one. And so this is very exciting to me, partially because it's a new layer of quantum mechanics, but also because of the way higher category theory works. There should be no reason why it stops here that I can see. It should just keep on going. So there'll be more layers yet to come. I'm trying to persuade somebody to work out the next layer of these kind of relations. No one, so far no one has taken me up on that challenge. I'm too busy to do it myself. but I think I shouldn't think it should not be actually that difficult. I will just say that if you like higher categories, there's work to be done. Although actually right now I think I have a student who may succeed in doing it, so maybe I shouldn't get you to do this. But there really should be a symmetric monoidal bicategory that has groupoid spans and spans of spans as its structure there, and that's something you should be able to prove to set up. It's like setting up the infrastructure of linear algebra at this categorified level. And two students of mine, Alex Hoffman and Mike Stay, have proved a sort of baby version of this back when I was stupidly thinking maps of spans were the correct thing. I had coaxed some students to prove this type of result in that case. It took a lot of work, so I feel I'm too guilty to try to say, now do it all over again with spans of spans. But luckily I think I have I've learned from some friends some ways to simplify the argument a lot so that it will be doable. Okay, so I'll stop there. Thanks.